Let's go ahead and take a look at some of the problems that we'll see possibly coming up on the exam by working through this practice exam. One of the things that I would encourage you to do is to draw lots of pictures to represent the probabilities in the areas that we're looking for. That's really helpful in finding solutions. So this says the probability that z lies between 0.7 and 1.98. So the first important thing to note is the letter z. Z stands for the standard normal random variable, and that means z is distributed normal with a mean of 0 and a standard deviation of 1. So here's a 0, 0.7 is to the right, and 1.98 is further to the right. Now the word here is between that we're looking for, so this is the shaded area. So of course there's several different ways that we could find this. Let's go ahead and look at our calculator first. So remember, with the calculator, we have a couple different functions that we can use under the second DISTR, and we want to look for normal CDF in this case because I'm trying to find the area on the normal curve. And so the lower bound that we can see over here is 0.7 because it's the lowest value in my shaded region. Now the upper bound is going to be the upper value in my shaded region, which is 1.98. And of course, because this is our standard normal random variable, the mean is 0 and the standard deviation is 1. So here we get 0.21811. Now that's an approximation. And remember, we might get a different answer depending on if we use the normal tables or if we use our calculators. So we'll use the normal table next to come up with a solution, and then we'll kind of compare those. So to use the normal tables, what we would do then is we would look up both values. The first one is 0.7, so that's 0.7580. So the left, the area to the left of 0.7 is 0.7580. So this area is 0.7580, but that's not the area we want. We want just this shaded region right here. So another thing we could do is we could look up the area to the right of 1.98 if we wanted, using symmetry, or we could look up the total area from 1.98 to the left and then subtract off this area. So let's go ahead and look up 1.98 on your normal tables. Oops, there's a T table, 1.98. So here's 1.9 going across 1.98 is 0.9761. So the area from here to negative infinity is 0. I already forgot. I think it was 0.9761. Yep, 9761. And then we would just basically subtract this area that we don't want, 0.7580, and we'll be left with this shaded area right here that we're interested in. So let's take 0.9761 minus 0.7580. So we get 0.2181 for the difference there. So this area is 0.2181. That's the shaded area. And that matches really well here. This is rounded to 4 places. This goes out further. So 0.2181 matches letter A, and so that's our first answer here. Now one thing that you could do before you even get started is you could get rid of B, because all probabilities are between 0 and 1, and this is more than 1, and this one's negative. So neither one of these answers are possible because they're not even probabilities. So again, a nice little curve sketch is very, very helpful here. Let's go ahead and pull in our next problem, number 2, and we're probably looking for a probability again. In number 2, we're going to assume a random variable x has a normal distribution, and they give us some information about the distribution, and we're supposed to find the probability of between again. So to get started here, x is distributed normally, and the mean is 137, and a standard deviation is sigma, not s here, but sigma is 5.3. So remember, this is mu and this is sigma. Now, again, we're trying to find probability. Well, we can throw out right away this first answer because all probabilities are between 0 and 1, and that one is more than 1. Now, if we want to find that x is between 134.4 and 140.1, let's go ahead and draw a picture. Now, there's several different ways to work this problem. We'll get started first of all by doing a quick little curve sketch. The mean is 137, the standard deviation is 5.3. We're going between 134.4, which is somewhere to the left, and 140.1, which is somewhere to the right. Now between is this area that we have shaded right here. Now, like I said, there's several ways that we could work this. Let's go ahead and jump to our calculator first. We would use second DISTR. Now we'd use normal CDF, which is the second option here. Now, if we think about the lower, we can see that the lower end of my shaded area is the 134.4. Now the upper end of my shaded area is this 140.1. Now the method what we're using right now, I don't standardize. I don't find the z-score. I just put in the mu and sigma of my distribution, which would be 137 for my mu. And my sigma then would be 5.3, and that's given. So we could just look this up directly, and we have our probability 0.4088. So that's one way we could do this problem. We'll also look at it a couple different ways. So this looks like it matches letter C pretty easily. And again, this is rounded 0.4088. Now this is the X scale. We could also look at this and standardize this to the Z scale. Now when we standardize, the middle of the distribution becomes a 0, and then I standardize each score. So I get Z equal X minus mu over sigma, if you'll remember. So for my upper, I'd have 140.1 minus 137 all over 5.3. Okay, so we want to go ahead and plug this into our calculators. 140.1 minus 137 divided by 5.3. So I get 0.5849. Now remember, this is the number of standard deviations I am above the mean, and our z-tables only go to the nearest hundredth, so I'll just round this to 0.58. Let's go ahead and standardize our other score as well. Now remember, the process of standardization means finding the number of standard deviations our observation is above or below the mean. Now this one is going to be negative because it's below the mean. So let's go ahead and divide, subtract first and then divide. So 134.4 minus 137. And then we do that subtraction, and then we'll divide that difference by 5.3. So I get a negative 0.49. Now again, because my tables only go out to 2 places, I'm just going to round this to 2 places. So using my tables, finding this probability then, probability that Z is between 134.4 and 140.1 is the same as the probability that Z is between negative 0.49 and 0.58. Now the way we look this up, this is the value that shows me that I'm looking up phi of 0.58. That means I'm looking it up in my table. And I'm going to subtract out phi of negative 0.49. Now the reason we subtract, same as our problem before, I find the area to the left of the upper number, and I subtract out the area to the left of my lower number, and I'm left with the area in between when I subtract this out. So let's go ahead and look up 0.58 on our normal tables. And remember, you can use either method that you want here. There's not a right or wrong method, so just pick a method and stick with it. So with our normal tables, we have 0.58. So here's 0.5 all the way across to 8.7190. and I subtract off my value of negative 0.49. So here's negative in this region, 0.4, all the way across 0.3121. Okay, so let's go ahead and subtract to find that difference. And when we find that difference, that's going to give us that probability. Now when I use the normal tables, I'm going to get a slightly different answer than when I use the calculator because the normal tables require that I round. So they should be in the ballpark, maybe 4.4069. So we can see that it's closest to this number. It's not any closer to either of these, so I'm going to pick the closest number. Now the directions on the test will indicate that you should always choose the closest value because of this rounding problem we have. So those are a couple different ways to work the same problem, and again, no matter whether you use the calculator or the standardization process, a quick little curve sketch will really save you some trouble. Okay, let's go ahead and pull in number 3. Number 3, I'm going to be looking at a percentile. Now if you recall, a percentile is basically splitting the curve up into percentages, and then instead of finding the area, I'm given the area and I have to work backward and find the standardized score. So if we read this, it says scores on a test are normally distributed. So we'll call the scores on a test, we'll say T is distributed normally, and the mean is 67.3, and a standard deviation is 9.3. The sign says find P sub 81, which separates the bottom 81% from the top 19%. So that's the 81st percentile really. So we're given the area here. So we're going to work this backward. Now I'm going to start with my normal curve, so I'm starting here with my Z curve. Now my 81st percentile tells me not 0.81 out here, but 0.81 on the inside, because my area is 0.81. So what we want to do then is we want to go to our normal tables and find the value that when I look it up, I will have 0.81 to the left. Now we can use our calculators for this as well, and we'll look at that process next. Need a normal table here. So 0.81, I'm trying to get to the closest that I can. 0.8, 850, 8106, I think here we have it here. So that's 0.88. That means I'm 0.88 standard deviations above the mean. So what do we do then is we work this backwards and we say, okay, Z equal X minus mu over sigma. Well, we know Z is 0.88. We don't know X, but we do know mu is 67.3 and sigma is 9.3. And then to solve for X, we multiply both sides through by 9.3. Because remember, whatever you do to one side, you do to the other. The 9.3's cancel. And I'm left with adding the 67.3 across, and I get X equals 67.3 plus 9.3 times 0.88. So let's go ahead and plug this into your calculator and see what we get back out. So we have 67.3 plus 9.3 times 0.88. We get 75.484. So this is the value that separates the 81st lower scores to the 19th upper scores. So for my X scale, my mean is 67.3, and then this standardized score converted into 75.484. So that's my answer. So 75.484, closest value would be B. Now a couple things to look at here. Before we even get started, we know my mean is 67.3, and I'm looking at the 81st percentile, so I have to have a score larger than 67.3. So right away, I could throw out these two values, and then I'm left, of course, with B and C to work from. Now, how do you do this on your calculator? Well, on your calculator, you're going to use the second DISTR, But now we're going to use inverse normal because we're given the area. So now the area to the left is 0.81 because we always work with the area to the left. The mean is 67.3. And the standard deviation sigma is 9.3, and that comes from what's given. So I get a similar value. So let's go ahead and paste that into the lecture. And we can see that it's not exact, but if we round it to the nearest tenth, I do get a matching solution. But this curve sketch is what makes that really easy to follow and read. And on the show your work problems on the test, you'll definitely want to make sure that you are using the curve sketch and showing all of these steps, or showing your calculator steps, so to get all of your partial credit, because those are worth a lot of points. Okay, let's go ahead and look at number 4 next. So number 4, again, we're trying to find probability. So the first thing that it would be a good idea to look at would be if all the probability values are reasonable. Now remember, probabilities always have to be between 0 and 1. And it looks like to me on this one, all of the probabilities are between 0 and 1. So there's none that I can just throw out right away. Okay, so this one, it says the lengths of human pregnancies. So lengths are distributed normally, and it has a mean of 268 and a standard deviation of 15 days. What is the probability that a single pregnancy lasts at least 300 days? Okay, so let's go ahead and roll out our distribution here. The mean is 268, and then here I am at 300 days. Now when I talk about at least, that means 300 or larger. So this is the area I'm looking for. So we could do this with our normal tables or our calculators. Let's go ahead and pull out our calculators first on this one. This one we're going to use normal CDF because I'm looking for area. So the lower value you can see is 300. And then my upper value is actually going toward positive infinity. And basically you just put in a really big number like 100,000 or 10,000. The mean is 268, that's given, and the standard deviation is 15, which is given as well. So that is my area, and then we'll see if we have a close value, and then we'll also find the same thing using the tables. So 0.01644. Okay, so that looks like closest to letter A. And so our calculator helps us find that value. Now for our normal tables, what I do is I compare this length distribution to the z distribution. Now remember, when we standardize, I have my value here of x minus mu over sigma. I'm trying to figure out what 300 is. I'm trying to figure out how many standard deviations this is above the mean. So I have 300 minus 268 over 15. Sigma is 15. So let's look at our z-score. And we have 300 minus 268. And that's divided by 15. So I get 2.13. So this is the number of standard deviations that score is above the mean. So really what I'm looking for here then is the probability that the length is greater than or equal to 300. But when I standardize, this changes to z greater than or equal to 300. Now remember, your tables give us the area to the left. So if I look up, I'm sorry, I have a mistake here. After I standardize it, that's not 300 anymore. That is 2.13. So if I look up 2.13 in my normal tables, 2.10123, 0.9834, that's the area to the left. So this probability, because I want the area to the right, I have to take 1 and I have to subtract off phi of 2.13. And we just looked at that up and it's 0.9834. And when I subtract 1 minus 0.9834, I get 0.0166. And you can see that this is very close to this value as well. So again, the directions, you probably won't find the exact value, but you'll find the closest value. Okay, let's go ahead and look at number 5. Same thing. We're going to be looking at finding probabilities. Remember, all probabilities are between 0 and 1. So if you get an answer that's not between 0 and 1, you probably have a mistake. Okay, so for this one it says the weights of the certain fish in a lake are normally distributed. So weights are normally distributed with a mean of 15 pounds and a standard deviation of 9 pounds. Now this one is a little bit different. It says 9 fish are randomly selected. So then they tell us that n equal 9. It says what is the probability that the mean weight, the x bar here, will be between 12.6 and 18.6 pounds. Well, what that tells us is the average of the weights then is distributed normally with the same mean, but the standard deviation is now sigma over the square root of n. So it would be 9 divided by the square root of 9. So W bar is distributed normal with the mu equal 15. Sigma square root of 9 is 3. 9 divided by 3 is 3. So this is still sigma over root n is equal to 3. Now I'm looking for the probability that the average is between, so this is W bar again, this is my W bar scale, 12.6, which will be somewhere to the left, and 18.6, which is somewhere to the right. So I'm trying to find this area that's shaded in between here. So we can go straight for our calculators, or we can use our normal tables. Well, this is the normal curve, and I want to find area, so I'm going to do second DISTR, and we'll go to normal CDF. Now my lower curve, or my lower value, I can see here is on the left of my shaded region is 12.6, and the region up here, the upper part, is 18.6. Now the mean is 15, that's given. Now the standard deviation is not just 9, it's 9 divided by the square root of 9, which is 3. So this is going to give me that area directly. So let's go ahead and paste this in and compare it with our possible multiple choice solutions. So it looks like we have 0.6731. We round this to 4 places. And that looks like it matches letter B. Okay, so number 5 would be B here. Now we can also do this by standardization. So if I look at this in terms of Z, remember the mean always standardizes to 0. Because I have a sample size here, now my formula changes to x bar minus mu sigma over square root of n. So let's go ahead and standardize 18.6 first, minus the mean of 15, divided by sigma over the square root of n. And I know it's 3, but I'm going to write that out just so you can see where the numbers are coming from. So let's go ahead and plop these into the calculator and see what we get back out. 18.6 minus 15 divided by, in parentheses now, and again I know that this is 3, but I'm just going to plug it in so I get in that habit. Get rid of that parenthesis. And I get 1.2. So that means I'm 1.2 standard deviations above the mean here. Now we're going to do the same thing for my other value, my lower value of 12.6. So I'm using the same formula, but now we're going to standardize 12.6, and because it's below the mean, it should turn out to be negative. So we have 12.6 minus 15, and then divided by, and of course I already know that this is 3, but I want to go ahead and plug it in so we can actually see the process of plugging it in correctly. Just be kind of careful about it, and I get negative 0.8. So that means I'm 0.8 standard deviations below the mean. Okay, so in order to find this area, I'm really looking for the probability that W bar, not X bar, is between 12.6 and 18.6. But when I standardize that, that means I'm 0.8 standard deviations below the mean up to 1.2 standard deviations above the mean on my X scale, or on my Z scale. So this is phi 1.2 minus phi of negative 0.8. Now the reason we subtract again is this whole idea of the area to the left, subtract off the area to the right will leave me with the area between. So let's go ahead and grab our normal tables. First thing we'll look up is 1.2, and that's 0.8849. And then we'll look up negative 0.8 for my lower value. So here's negative 0.8, 0.2119. And let's see what we get here when we subtract. 0.8849 minus 0.2119. And I get 0.673. So here's another way to get to that solution. Now you can see the closest value is 0.6731, and it's very, very close. And so whether I use a calculator or my normal tables, I get a similar answer. This is number 5. Okay, let's go ahead and look at number 6. Number 6, we are given some information about the margin of error, a level of confidence, and something about a proportion. And then we're asked to figure out how many people we should sample to stay within these specific parameters. So this is sample size. So sample size formula is z squared p hat q hat over your margin of error squared. Now remember, for here you always round up. No matter what your answer is, you always round it up. So my error is pretty specific. They gave us that as 0.09. Now p hat is going to be given in this case. I don't have to divide anything, it's just given as 0.87. Q hat is the complement, meaning what makes this sum to 1, which would be 0.13 in this case. And then I need something about the z-score. The z-score from a 95% confidence level, let's go ahead and review, that's going to come from the normal distribution. So that means 95% is centered about the mean. And if I take 1 minus 0.95, I get 0.05 and split it between two tails, and I get 0.025. So if I look at 0.025 in my normal tables, so I'm going to get the closest that I can here. I have, closest I can get is 1.96, plus or minus 1.96. So it would be 1.96 standard deviations above and negative 1.96 standard deviations below. Now, if you want to look these up, you can also. Now, if we're going to use our calculators to find this, we would use the second DISTR. And again, we're going to go after this curve sketch that we have right over here. So we go after normal CDF because we're trying to find a standardized score. Now the upper and lower areas that I'm looking for here, lower area would be this negative very large number, so like negative 100,000 or something like that. And then this would come up to, oh, I forgot, I worked this one backward. We didn't know plus or minus negative 1.96, so we need to clear this out. And we need to work this backward and use second DISTR inverse normal. So for the inverse normal, I know the area is 0.025. I forgot what we were working backward. I found the other value from the table already. Mean is 0, standard deviation is 1. And we can see that I get negative 1.96 here, so that's where that comes from. So when we're given area, we work inverse normal. So that's where that value comes from. And then we just go ahead and plug this entire n into my calculator. So in the numerator, I'd have 1.96 squared. And then times 0.87 times 0.13. So that's the numerator divided by the denominator squared, which is 0.09 quantity squared. Okay. Now remember, we always round up to the next value. If we round down, I wouldn't quite have the sample size needed to meet the criteria there. So in this particular case, when I round up, I would round up to 9, I would get 54. And that would be our answer for letter C. So again, I get 54. So my sample size should be about 54. It can't be lower, because otherwise I wouldn't meet that particular confidence level or that margin of error that was given to me. Okay, let's go ahead and look at number 7. In number 7, we're working with a proportion. It says use the given degree of confidence and sample. Okay, for this next problem, we're trying to find a confidence interval for a proportion. So the first thing that we should do is we should write out the correct formula and then kind of work from there. So the correct formula for the confidence interval for a proportion is going to be p hat plus or minus your z, your confidence factor, p hat q hat over n. Now this bit is underneath the square root sign. So let's go ahead and look at what we're working on here for p hat. P hat is going to be 111 over 298 because we're looking for the true proportion of all college students who own a car. So our sample, 111 out of 298 owned a car. So then I'll have a z-score here, and then I have a big square root. Now over here, in order to find q hat, we take 298 minus 111, which would be 187, and the denominator then would be n, which is 298. Now the z value, let's go ahead and talk about this z value before we go too much further. So if I'm 99% confident, one quick way I could work this is doing a curve sketch, of course, is very helpful. And again, in the test you're going to be asked to show your work, so show all these curve sketches so you can get lots of partial credit. Now I have 99% in the middle, which means I have 1%, half of that which is in each tail. So half of 1% would be 0.005. So you take 0.01 divided by 2. And then on your calculator, if I can find a calculator here, we would have second DISTR, and then we'd have inverse normal because we know the area is 0.005, mean is 0, standard deviation is 1, and we get negative 2.576 here. So if we use our calculator, we're going to get plus or minus 2.576. Now if we use our normal tables, we're going to get 2.575. So if we look up the closest that we can get to 0.005, we can see that it's right in between these two values, and then read down, this suggests that we use negative 2.575. Doesn't matter which one we use, I'm just going to go with the normal tables here. Because remember, we always answer what's closest. So let's go ahead and start with 111 divided by 298. Now notice all of my confidence intervals up above round to 3 places. So let's go ahead and round to 3 places. We get 0.372. And then we have 2.575 times the square root of all of those values. So 111 divided by 298 times 187 divided by 298, and that's divided by 298, and that is square rooted and then multiplied by 2.575. So I get 0.072 here. So my lower bound is going to be 0.372 minus 0.072, less than the mean, less than 0.372 plus 0.072. So our lower bound, 0.372, minus 0.072 is 0.3. And then my upper bound is going to be 0.372 plus 0.072. And you get 0.444. And that's closest to letter D. Now if I would have used plus or minus 2.576, these values would have been off slightly, but they still would have been closest to letter D. Okay, let's go ahead and look at number 8. Now on number 8, I'm given raw data. So from this raw data, I'm going to have to go ahead and punch those into my calculator into a list and find mean and standard deviation based on a sample. They're not based on a population, so we have to make sure that we understand we're working with X bar and S here, and not mu and sigma like we have in the previous problems when we're talking about the mean. So this one says use the given degree of confidence in sample data. So right away we know we're working with a sample because we have sample data to construct a confidence interval for the population mean mu. It says assume that the population has a normal distribution. Okay, so the football coach randomly selected 10 players, so we know n equal 10, and timed how long each player took to perform a certain drill. So what we know here then are the drills are distributed normally. So we know normal here because it told us right up here. Okay, and what we want to do is, because we assume the underlying distribution is normal, sample size is 10, what that happens in is D bar is distributed with a T distribution with 10 minus 1 degrees of freedom. But before we can do any of these things, we need to find X bar and S based on our sample data. So X bar, and remember S is our sample standard deviation. Now it's been a while since we've used our stats menu. So let's go ahead and review that. So stats, edit. Now I already have data in L1, so I'm going to scroll up and hit clear and enter. And then go ahead and enter my new data. So I'm going to just go ahead and enter this very fast. Make sure you don't make any mistakes, because if you do, they're going to throw off your X bar and your S, and then your final answers may not match any of the given options. Now once you have your data entered, remember we go back to the stats menu, and then we arrow over one to the right, and we choose calc, one variable statistics. Frequency, I don't have a frequency list because each of the data points is listed. And then these are the values that I'm going to use for my X bar and S. So let's go ahead and clip these out of here. Now a lot of these I don't even need. There's only just a few of these that I need. Okay, so it looks like to me X bar is 5.58, which looks reasonable. And S is this large value, 0.297. 396,107. And I'm going to keep that all the way out, because if I rounded this too much, it's going to throw off my final answer and maybe throw me into one of the other options that's incorrect. So you have to be very, very careful about rounding. Okay, so to get started here, I need a confidence interval, and it's a confidence interval for the mean, but I have to use the T distribution. And the reason I have to use the T distribution is that sigma is unknown. So quick note, sigma unknown, use T. Okay, so sigma unknown, use T. So if we're building a confidence interval, we want X bar plus or minus some level of confidence, which I'm going to call my T value here, and then I have S over the square root of n. So let's get to building on this. So we have 5.58 plus or minus. I'm going to leave a big gap here for this T value. Figure that out in a second. And then S. And again, I don't want to round that, over the square root of n. In this case, n is 10. Now for this T value, let's go ahead and review where that comes from. This is the T distribution with 9 degrees of freedom. That's the important part here, is that 9 degrees of freedom. The level of confidence that we have is 95%. So I have a 95% level of confidence. Okay, so let's go ahead and have a look. If I have a 95% level of confidence, that means 5% is split between two tails. So in each tail we have 0.025. We can use our t-tables. So we'd look under 9 degrees of freedom. Area in two tails is 0.05. Area in one tail is 0.025, so that's the column. 9 degrees of freedom would be 2.262. That's what we want to use for our value. Now we can also use on your calculators the inverse t. Now some of you have programmed this in and you'd look under the program button. Some of you have it under second DISTR and you'd use inverse t. The area to the left was 0.025. Sorry, 0.025. And the degrees of freedom are going to be 9. So we should get a value that's pretty close. It's not going to be exact. In this case, it is very close. So that's another way to find your t value. If you don't like using the tables, you can use it on your calculator. So I get the 2.262. So we have 5.58 plus or minus. Okay, so let's go ahead and plug this into your calculators and get our margin of error. So that would be 2.262 times 0.297396107 divided by the square root of 10. And so for here, for my confidence margin of error for this confidence level, I get 0.2127. Now notice all these values are just rounded to the nearest hundredth. So for my lower endpoint, I'll have 5.58 minus 0.21. So I get 5.37 is less than the mean, is less than 5.58 plus 0.21 is 5.79. So this is my distribution. So if we look back up at our options here, that looks like it's closest to letter A. Closest to letter A. And again, we want to choose the value that's closest. So that one we knew we had to use the t-distribution because sigma was unknown. Okay, let's go ahead and look at number 9. Here we're starting hypothesis testing. Now remember, with hypothesis testing, you need to make sure you show all the steps, especially for the show your work problems. So for this one it says express the null hypothesis HO or H naught and the alternative hypothesis H1 or HA in symbolic form. Use the correct symbol, mu for mean, P for proportion, sigma for population standard deviation for the indicated parameter. Okay, so to get started here, it says the Carter Motor Company claims that its new sedan, the Libra, will average better than, so here's better than 23 miles per gallon in the city. Use mu, the true average mileage of the Libra. So when we're talking about HO, remember, HO always has an equal sign. They're telling us to use mu, better than is greater. So 23 miles per hour is the number that they give us. So let's go ahead and see which HO and HA match here. Looks like it's letter D. So again, it's still good to write these out to get started, because sometimes some of the language would be a little bit confusing. And so when you write these out like you would during your 6-step process or however many steps we have, it kind of gets your mind going in the right direction. So for this next one, it says find the p-value. Okay, so that means we're going to be using some tables here. It says a manufacturer claims that fewer than 6% of its fax machines are defective. Well, right now I see that we have a percentage, so I think we're probably using like a p hat or a proportion that's testing p. So for step 1 here, I'm going to state HO and HA. So I think we're working with p here. So again, HO always has the equal sign. Now this one says fewer than, so that's less than, and 6% is 0.06. So here's my HO and my HA. Now on this one, alpha, our level of significance, is not given because they're not asking us to make a decision, they're just asking us to basically find our p-value. So for this example, alpha is not given because we don't decide anything at the end. Now step 3, I go ahead and calculate my test statistic. Now my test statistic is going to be z equals p hat minus p divided by pq over n square rooted. Now that square root sign goes to the pq and the n, so be very careful about how you write that. Now p hat in this case says we have a simple random sample of 97 such fax machines, 5% are defective. So they're giving us right now what p hat is. So p hat is 0.05. P is 0.06, square root of 0.06, 0.94, divided by n. N in this case is 97. Okay, so now we have to be really careful about how we plug this into the calculator. So in the numerator I have the difference, 0.05 minus 0.06. 0.05 minus 0.06. Divided by, okay, now I have the square root, 0.06 times 0.94, that's P and Q, divided by 97 is my sample size. And again, all of this is underneath the square root sign, that's very important. So this is my test statistic, negative 0.4147. And what that's saying is I'm negative 0.4147 standard deviations below the mean. Now the question is that too far below the mean? And so we're going to help answer that question by finding the p-value. So here we could say 4147. Okay. Now, if you're going to use your normal tables, you would probably just go with the negative 0.41 here. So the fourth step is to go ahead and calculate the p-value. So calculate the p-value. Nice little picture here. Mean is 0. Here's my p-value, negative 0.4147. My alternative hypothesis tells me that this is a left tail test. So this area shaded to the left is my p-value. Now there's several different ways I can find this. Let's go ahead and look at our normal tables first. So if I grab my normal tables and I look up negative 0.41 on the left hand side, negative 0.41, I get 0.3409. So 0.3409 is actually a very large p-value. It doesn't mean anything's wrong, it just means I have a big p-value here. So 0.3409. Now the way I got that is I looked up negative 0.41 on our tables and I got that value of 0.3409. So phi of negative 0.41 is 0.3409. Now on your calculators you go to second DISTR. Now on this one we're going to use normal CDF because I'm looking for the area. Now my lower bound is some very large negative number, maybe negative 100,000. My upper bound is this negative 0.4147. And the mean is 0 and the standard deviation is 1 because I just forced that to happen when I found my test statistic. And I get 0.3392. It looks like it's close. Okay. So this is the information that I would get using your calculator. Now you can see that they're not exact, but they are pretty close. And so if we come back up and look at our options that are closest, it looks like to me, for this one, B is the closest. Not all that close, but it's the closest one that we have here, and that's letter B. Okay, so again, we don't want to round till the very end because we don't want to have any more rounding error than necessary. Okay, next problem. We are still finding the p-value. So for this one, it says to find the p-value. A random sample of 139 40-year-old men contains 26% smokers. Find the p-value for a test of the claim that the percentage of 40-year-old men that smoke is 22%. So even though they're not asking us for this information, I'm going to get started by writing our HO and HA, because that helps us determine the direction of the test. So in this case, I'm looking at percentages again, so I have P's equal sign always goes with HO. Now this doesn't say greater than or less than, it just says we want to test the claim that it's equal to. So the alternative is that it's not equal to. So this is 0.22, which is the same as the 22%. Second, alpha in this case is not given because they're not asking for a decision, they just want us to find the p-value. The third step is to go ahead and calculate the test statistic. So the test statistic is the same as ours was last time, z equal p hat minus p divided by pq over n square rooted. So p hat in this case is 26%. They give us that value. So 0.26 minus 0.22. Now my denominator at 0.22, 0.78 for q, and then my sample size was 139. Now again, you have to be careful about how you enter this in your calculator, because you need to make sure everything is correctly underneath that square root sign. So I want to put the numerator in parentheses to make sure I'm dividing correctly. Here I'd have 0.22 times 0.78 divided by 139. And I get 1.138 here for my test statistic. So that means I'm 1.138 standard deviations above the mean. Now the question is that too far above the mean to deem acceptable or not? And the p-value kind of helps us decide that. So I'm going to use 1.14 here. I'm going to round this to the nearest hundredth this time. Okay, so next thing we want to do is we want to go ahead and find our p-value. So this is a two-tail test. So I have 1.14. So I'm looking for this area as extreme or more extreme. But this is a two-tail test. So I need to remember that we double the probability. So this is half of p. Okay, so now we can grab our normal tables and we can look up 1.14 if we want, but that's going to give me this area over here, and that's not the area I want. So due to symmetry, I'm going to look up negative 1.14. And I know that this 0.1271, the area to the left of the negative 1.14 will be the same as the area to the right of 1.14 because of symmetry. So p would equal 2 times 0.1271. Okay, so 2 times 1271, I get 0.2542. Okay, so we're trying to get to the closest that we can here, and it looks like to me that's closest is 0.2671. Now again, we're going to have rounding error depending on, you know, how we ended up rounding here or here. So we have to be really careful about choosing the closest value. We don't want to over round. Now we could also find this on your calculators. We already know the standardized value, so what we need to worry about here then is the area. So I'd use second DISTR, normal CDF. My lower value here is 1.14. Looks like my calculator's stuck. Just a second. Okay, so I got my calculator going again. So we go second DISTR. We're going to go to normal CDF. Now my lower is 1.14 here. My upper is some very large positive value that goes toward infinity, so maybe 100,000 or 99,000. My mean is 0 and my standard deviation is 1. But remember, this is not my final answer. I need to take this times 2 because we have a two-tail test. So my overall p-value then will be the result after I take this times 2. And we can see here that we get a very similar answer of 0.2542 that I did here. And up here on my answers, the closest value is 0.2671, which is letter A. Okay, let's go ahead and look at our next problem, number 12. This is definitely a larger, longer problem word-wise, but they're actually asking us to draw a conclusion. So we're not running through an entire hypothesis test. We're kind of shortcutting it and saying, okay, well, if you were told that we rejected or failed to reject, what does that mean in terms of the problem? Okay, so number 12, let's go ahead and read through it. It says formulate the indicated conclusion. So we're stepping to the last step of our series of hypothesis testing steps. Be sure to address the original claim. Okay, so before we get going too far, I want to look at the original claim, HO versus HA. Okay, so let's go ahead and read through this. An entomologist writes an article in a scientific journal which claims that fewer than 16 in 10,000 male fireflies are unable to produce light due to a genetic mutation. So we're looking at a proportion, 16 in 10,000. So remember, P is proportion. The equal sign always goes in the null hypothesis. Let's go ahead and look at the alternative hypothesis there. Fewer than, so we're looking at less than, and 16 in 10,000. So if we look at 16 divide 10,000, we get 0.0016. So let's go ahead and note 16 over 10,000 is 0.0016. Okay, now we're not doing step 2, alpha, not given. Step 3, test statistic, cannot calculate because I don't have any data. Test 4, step 4, I can't find a p-value because I don't have a test statistic. Okay, but step 5, now that's interesting. Step 5, let's go ahead and read through here. Assuming that a hypothesis test of the claim has been conducted and that the conclusion is to reject the null hypothesis. So the decision was to reject HO. And so if we reject HO, that means we have evidence in favor of HA. So we reject HO in favor of HA. Okay, it says state the conclusion in non-technical terms. So let's go ahead and read through these. The beginning part is there is sufficient evidence, there is sufficient, there is not sufficient. So it looks like we could throw 2 of these out right away. Also, we have 2 that say greater than 2 that say less. So this, writing out the null hypothesis, I need one of the 2 that say less. So the greater than ones we can throw out just because the greater than part doesn't fit with our null hypothesis. So there is sufficient evidence to support the claim that the true proportion is less than 16 in 10,000. Well, we rejected HO in favor of HA. So we said we have evidence for HA, which is letter B. So this is letter B. So there is sufficient evidence to support the claim Okay, so to support the claim that the true proportion is less than 16 in 10,000. Okay, so even though it didn't ask us for all the steps, I think that writing out your HO and then kind of seeing where you're at in the process will help you answer this type of question correctly. Okay, let's go ahead and look at number 13. Try that again. Okay, now number 13, we're still working with hypothesis testing. This one says determine whether the hypothesis test involves a sampling distribution of means that is a normal distribution, a t-distribution, or neither. So for 13, let's go ahead and look and see what we have. So first of all, what we do know is our first step, HO, we're working with the mean. Mean is 72. Now, they don't give us an HA, but we do know that it's a mean. We don't know if it's less than or greater than. We're just not sure. Now, step 2, alpha is not given. Step 3 is our test statistic. Now, what they're asking for here is basically to work with the test statistic. The question is, what test statistic do we use? Do we use a T or a Z? So let's go ahead and look at what we have. Now, the claim is about the mean. Sample size is 23. So X bar is 109. Sample standard deviation is 15.1. The sample data appear to come from a population with a distribution that is very far from normal. Okay, and sigma is unknown. So first of all, this kind of says down here, if we know S, sigma is unknown. So as soon as sigma is unknown, we know it's not the normal. So we can throw that one out. Now, because the underlying distribution is far from normal, we can say that it's not the T. It's not the T distribution because in order to use the T distribution, my underlying has to be normal. So it's not the normal, it's not the T, so it's neither. So that's letter A. So again, you need to remember, sigma is unknown. You have to eliminate the possibility of the normal distribution. And then you have to check that the underlying distribution is normal in order for me to use the T distribution. Now these last two problems are short answer. That means these are the show your work problems, and of course we've been showing work for all of these problems. But you really need to make sure you show all of your steps, show your curve sketch. Go ahead and show what you plugged into your calculator in order to get lots and lots of credit. On the test, I believe these are worth 20 points each. So that's a lot of points, so make sure you show your work. Okay, so it says identify the null hypothesis, the alternative, test statistic, p-value, conclusion. So they want you to do like the whole 9 yards on this particular problem in terms of the hypothesis testing. So we're going to run through this step by step. So we'll have HO versus HA. So it says the health of employees is monitored periodically by periodically weighing them in. A sample of 54 employees. Okay, so we have n equal 54. I'll kind of sketch these out over here. Has a mean weight of 183.9 pounds. Assuming that sigma is known, I guess I don't need to write known, I can just go ahead and put in the value here. So let's assume sigma is known and it's 121.2 pounds. Use an alpha of 0.10, 10% level of significance to test the claim that the population mean, so that means we have mu here, equal always goes with the null, is less than 200 pounds. Okay, so these numbers always match. So here's my start. Now my level of significance is step 2, and that was given to me, is 0.10. Okay, let's go ahead and look at step 3. Step 3 would be my test statistic. And then from our test statistic, we have to decide which distribution we're using. So if we go back and look at the information that's given, it doesn't say anything about the underlying distribution being normal, but my sample size is large, sigma is known, so that tells me I can use the central limit theorem. So again, sigma is known and is large, so I'm going to use my z statistic. And so my z statistic is going to be x bar minus mu, and in this case, sigma divided by the square root of n. So x bar is 183.9, mu is 200, sigma 121.2 divided by the square root of 54. Now again, you have to be very careful about how you plug this into your calculator in order to get the denominator correct. So in the numerator, in parentheses, I have 183.9 minus 200, close parenthesis, divided by, open parenthesis, 121.2 divided by the square root of 54, and then you can arrow out and close those parentheses. So we got to make sure you have all of this in parentheses in the numerator and denominator. So this value that it gives me here then basically says I'm negative 0.976 standard deviations below the mean. And what we need to figure out then, is that too far below the mean to accept or fail to reject the null hypothesis? Reject or fail to reject the null hypothesis. So this is negative 0.976. I'll take it out to 3 places. Okay, next thing we're going to want to do is to calculate the test statistic. So when you're showing your work on the test, make sure you show all of these steps and label them. So next step is to calculate the p-value. Now this is a single tail test. In fact, it's a left tail test. So this is negative 0.976. And so it's a left tail test, so I'm looking for this shaded area as my p-value. So again, this is a left tail test. Okay, so there's several different ways I can find this. Because I'm using the normal distribution, I could use the normal tables. And I'd look under 0.976 would round to a negative 0.98. So negative 0.98, 0.1635. So if I look up phi of negative 0.976, I get 0.1635 for my p-value. Another thing that I could do is I could use my calculator and use that second distr function and under normal CDF. Now in this case, the lower is going out here toward negative infinity, so negative very large number, like negative 100,000 or something. And the right bound of this shaded area is negative 0.976, so negative 0.976. The mean is 0 and the standard deviation is 1 because I standardized that using the test statistic. And I get a similar value here of 0.1645. So it looks like my p-value, I'd be safe to say, is 0.1635 or 0.1645, either one. I'm just going to go ahead and stick with this for my p-value. So again, as you show your work, number these, label these, and circle each of the answers in between for your test statistic and p-value, so it makes it easy to see where your path is leading. Okay, now number 5 is going to make a decision. This is where we reject HO, and if we reject HO, that's if P is less than or equal to alpha, or we fail to reject HO, and this is where P is greater than alpha. Well, let's recall our p-value is 0.1635, and the alpha they gave me, let's go check that out, is up here at 0.10. So we have P greater than alpha. 0.1635 is greater than 0.10. So our conclusion here then would be to fail to reject HO. Last step is to draw some sort of conclusion. Okay, forgot what this problem was about. Let's go ahead and run back to the top and have a look. Okay, health monitors, the average weight is equal to 200 or less than 200. Well, we failed to reject HO, so that means we don't have any support for the alternative hypothesis. So we'd have to say there is not sufficient evidence, or the data does not support the conclusion that the average weight of employees is, so it didn't support this. So it doesn't support the conclusion that the average weight of employees is less than 200 pounds. And we can see from our data that we were given that it's very, very close to 200 pounds. It's slightly less than 200 pounds, 183.9. But when we talk about a group of 54 people having this average, they're saying, you know what, it's not far enough from the mean for me to say that for the entire population it's actually less than 200. It's still just a little bit too close. So that's the conclusion that we draw here. And again, on the show your work portion of the test, it's so important that you show every single step. This problem that we did right here, if it showed up on your test, it would be worth 20 points. So again, it's really important that you show all the steps so you can get lots of partial credit. Okay, let's go ahead and look at our next show your work problem. And again, on these show your work problems, you need to make sure that we do just that. You show lots of work. Justify every step, just justify every decision and every calculation. Okay, number 15. It looks like we have a raw data set, so that will be interesting. So before we even get started here, let's go ahead and look at the raw data. So here we have a sample of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And we should be able to get an X bar, which is our sample mean, and an S, which is our sample standard deviation out of this. And then we'll start the problem. Okay, so we'd grab our calculator, and remember that's under Stat, Edit. We'd go up and clear the list, and go ahead and enter our values. So again, be really careful about how you enter these. If you make any mistake, what will happen then is that will throw off all of your values, and then you'll end up with the whole problem wrong. And 563. Okay. So now I go back to Stat, Calc, one variable Stats, and my list is my list one, a frequency. I don't have a frequency list, and there's all my data. So let's go ahead and pop this in, and then get our summary values off of this. Now remember, we don't want to round till we get to the end of the problem, so we need to be aware of rounding. So my X bar here is 537.1. And again, I don't want to round that value. And here my sample standard deviation S is 20.701315. 04. I guess I can tack on an 04 there. Now, I don't know sigma here. Sigma was not given. And let's go ahead and have a look here. This says, assume that the sample has been randomly selected from a population with a normal distribution. So I have a normal distribution, sigma unknown. So that means I use the t distribution. Now what's happening here is because sigma is unknown, that changes the variability to follow more of a t distribution than the normal distribution of the means. So let's go ahead and get started listing all of our values. First step is to state the null and the alternative hypothesis. We're talking about means here, so we're going to use mu. Equal always goes with the null hypothesis. The mean time between failures is greater than, so that's greater than 520 hours. Second step is to list the level of significance, which is 0.05 in this particular case. Next step is to go ahead and calculate the test statistic. Now, just as we were talking about above, with the test statistic, I'm going to be using the t distribution. So I have x bar minus mu s over the square root of n. X bar in this case was 537.1 minus the mean, 520, and then s is this value up here. That's that 20.701311504 divided by the square root of my sample, which is 54. Now again, we have to be very, very careful about how we plug this into the calculator. The entire numerator needs to be in parentheses. So I have 537.1 minus 520 divided by, make sure this is in parentheses as well, 20.701311504 divided by the square root of 54. Arrow out, close parenthesis, and this is going to be my critical value t. I think I have a mistake here. Let me go back and check. Okay, so let's backtrack through. Oh, I see my mistake. My sample size n is 10, not 54. I have no idea where that came from. So let's go ahead and use this value of 10 again and plug it into our calculators. Now again, it's really, really important that you have parentheses around that numerator. So you have 537.1 minus 520 divided by your s in parentheses 20.701311504 divided by the square root of 10. And then we're going to arrow out. So we get 2.612 for our t value here. 2.612. That's our test statistic. Now again, when you're doing the show your work problem, show these step by step. Okay, 4, we're going to go ahead and calculate the p-value. Now to calculate the p-value, we need our test statistic. 2.612 is a t-value, and we need that this is a right tail test. So a curve sketch is helpful. Now another thing we need with the t is we need to know our sample size is 10, so our degrees of freedom are going to be equal to 9 in this case. So this is the curve that we have T9, degrees of freedom. Mean is 0, 2.612. It's a right tail test, so I'm shading in this area right here, this right tail test. So I'm looking for this area. Now if we go and look on our t tables, the best we can get is an approximation. So if we look under 9 degrees of freedom, what we're trying to get is the closest value to 2.612. Well, 2.612 is in between 2.262 and 2.821. So if I come up here, that means my p-value is somewhere between 0.01 and 0.025. So that's the best that my tables can give us, is between 0.01 and 0.025. Now, both of those are less than alpha, so that's good. So for my table, the only thing that they can give us is my p-value is between 0.01 and 0.025. That's not ideal. We want a little more accurate value than that. Okay, now it will answer the question in this case, but if we can get more accurate, we should. Now if you programmed in the inverse t distribution, you'd look under program, or if you have it in your calculator already, you'd go under second DISTR, and we go to inverse t. Now the area, I'm sorry, we don't want to go to inverse t, we want to go to TCDF. So we go under second DISTR, TCDF, which is option 6 here. So my lower would be this value of 2.612, And then my upper is going to be some very large number toward positive infinity. And the degrees of freedom we just talked about were 9. So my TCDF gives me my area of 0.014. Now this is more accurate than a range of values. So let's go ahead and paste that in. So again, the table, the best we could do is between 1 and 2.5%, but we can see here from our TCDF, which all of your calculators have, I believe, that my p-value is equal to 0.0141 if we rounded it to 4 places. Okay, so that's my p-value. So p equals 0.0141. Okay, next thing I want to do is I want to make a decision. Remember, I have 2 decisions I can make. I can reject HO or I can fail to reject HO. So I will reject HO in favor of HA if P is less than or equal to alpha, and I will fail to reject HO if P is greater than alpha. So let's see what we have here. Remember, our p-value was 0.0141, and my alpha for this problem, I have to scroll up and look, I think it was 0.05. Yep, alpha is 0.05 up here. 0.05. So we can see pretty clearly here that we have p less than or equal to alpha. So 0.0141 is less than or equal to 0.05. So the decision that we would make here is to reject HO in favor of HA. Okay, last step is to draw a conclusion. Now again, on the show your work problems, you need to make sure you show all of these steps and do a good job with that conclusion. Now we rejected HO. So what we have here, and I have to go back up and check again. I always forget what the original problem was. These get so long. Original problem was, in tests of a computer component, it is found that the mean time between failures is 520 hours. We're trying to test a claim that for the modified components, the mean failure time is greater than 520 hours. So we are trying to see if we have any support for this. Remember, we rejected HO in favor of HA, so it does look like we have support that the new mean time is greater than 520 hours. So the data supports the conclusion. That the mean time between failures is greater than 520 hours for the modified component. So basically we have support for the modified component being an improvement. So again, on the show your work problems, please show every single step. Again, this problem would have been worth 20 points on the test, so you want to make sure that you show all of the steps so you can get all of the partial credit. It's very, very important. Good luck going through this. I know it was a long step-by-step process, but these are very long problems. It's good to know how to use your normal tables, your t-tables, as well as your calculator, so you can double check your work. Good luck, and as usual, bring your questions to class. If you have questions, you can also go to the Math Center or stop by my office.